Hello, today we are going to cover the third chapter of the second part of the course dealing with dynamic simulation using HDS. This third chapter deals with the way to move from a steady state simulation to a dynamic simulation, and it is probably the most important part of the course. Here you have available class notes for the development of the exercises we are going to develop in class. All the individual steps are carefully described so that you don't need to take notes. And when a part of the example is completed, the name of the file containing these improvements is specified in the notes. So, in that way that if you get lost at any time during the development of the course, for example, if you want to start the part corresponding to the reactor level controller and you do not have available the previous file, you only need to download the previous example, in this case, example D. Okay, we are going to start from the very beginning, and so you need to start to download the first example. All examples are available in this folder, and you need to click on the first one, example 3A. I have already downloaded this file, and it's here open in my HDS file. The system corresponds to a reaction process. I'm going to minimize this bar. A reaction process where propylene oxide reacts with water, the mixture of reactant is fed to the reactor, and here both react to produce a propylenglicol. This is an exothermic reaction, and that's why a cooling stream is required. The reactor has two exit streams, a reactor vent that, as you can see here, the molar flow is 0. That means that it is empty, but the steady state simulation requires that we connect to stream, and the reactor products, which is the liquid stream containing all the material with a total molar flow of 280 kilomoles, containing the unreacted propylene oxide and water and the propylenglicol which has been formed in the system. This process is already working in a steady state and no errors are reported in the status messages. Now we want to move and to do the dynamic simulation of this process. In the steady state simulation, many simplifications are allowed. For example, no control valves are required because when you specify a molar flow, this molar flow is established. However, when you move to dynamic simulation, this is not true, and if you want to provide a constant molar flow of propylene oxide, you will be required to introduce a control valve and a flow controller to regulate the system. We need now to introduce all these modifications. One of them, for example, I said, corresponds, for example, to the mixer. In a steady state, the mixer does not require any specification at all. However, this specification is set by default by HDS. It is here in the parameters menu, and it says that the pressure in the outlet stream is calculated as set the outlet to lowest inlet. This means that, for example, if I show pressures here, shift P, I have specified a pressure of 1.1 bar in the propylene oxide feed, 1.2 in water, and the system calculates the lowest pressure, 1.1, at the outlet pressure stream. Well, this is done by HDS, but this is not in real life, because if you connect 3 pipes to a mixer, in the real process, all pressures are automatically equalized because some flow is produced from high pressure pipes to low pressure pipes until equalized pressure is obtained in all the systems. In a steady state, this behavior is allowed because it is supposed that before building the real plant, you will introduce the valves and the modifications required to ensure that all pressures are the same. However, in dynamic simulation, you need to incorporate this condition. For that, you need to change the mixers from the default value, set outlet to lowest inlet, to the condition equalize all, make all pressures equal in the system. What's the problem? An error has arisen, this error here. It corresponds to a consistency error. A consistency error means that you have tried to specify more variables than allowed. That is, you have more specifications than degrees of freedom in the process. Here all the information is reported. The name of the inconsistent variable is the pressure of the material stream water feed. The pressure of this stream, 1.2. Why? The answer is in the bottom of this form. This value has been calculated by two different ways. A first calculation, 1.2 atmospheres, which has been a specified value. This is the value of pressure that we have specified here. But later, a new calculation has calculated a different value, 1.1 atmospheres. This has been calculated by the mixer, and it corresponds to the option we have selected here. We have forced the mixer to equalize all pressures, and it has assigned to the outlet and water inlet streams the pressure of the propylene oxide stream. And these values are not in agreement. How can we solve this situation? We close the consistency error, we open the water stream specifications form, and we just delete the pressure specification. Now the number of specifications is in agreement with the number of degrees of freedom. However, the error still remains. Why? Because calculations has been stopped when the consistency error appeared. You need to go to the menu bar and activate calculations again. Okay, as you can see now, the status is green, there is no error present in the status panel. And as you can see here, the only pressure which is specified, the only value with a star, is the one corresponding to the propylene oxide stream. The others do not have a star, that means that they all are calculated values. Okay, this is one of the modifications that you need to do to move to dynamic simulation. But there are others. Fortunately, you don't need to do all of them by yourself, because HYSYS has an assistant available which can help you to introduce these modifications and to specify them. This assistant is available in the option of the menu bar, Dynamics, Dynamic Assistant. If you click here, HYSYS will review all the specifications and will make a list of suggestions and changes to be introduced in the simulation before moving to dynamics. In the first tab, General, you have a list of the different items to be covered. These items are later described in the next tabs of the form. You can also access them just by double-clicking on each of these items. For example, the first one, Disable Stream Pressure Specifications. If you double-click, you see that the system proposes you to remove pressure specification in propylene oxide stream. Okay, this does not make sense, because if you remember, in our last class, when presenting the fundamentals of dynamic simulation, we said that the number of pressure, flow rate, specifications that we can do in any system is equal to the number of inlet and outlet streams. In our case, 2 inlet streams, 2 outlet streams, that means a total of 4 specifications. And the recommended values were not to specify any flow rate at any point, because usually this is not possible to be ensured, but to specify pressure at 4 different places, and the recommended places are exactly the external and the external stream pressure at these 4 points. So this recommendation of removing pressure specification in propylene oxide, it seems it's not reasonable. However, don't consider. It doesn't care if you activate this modification or let it as it is, because HDS is going to maintain it. The reason is that HDS is going to insert a new valve in this stream, and the pressure will be specified in the inlet new stream. The second, if you go to general back, the second recommendation is to disable stream flow specifications, double click, in streams propylene oxide and water feed. You can see that propylene oxide has a specified flow rate of 68 kmols per hour, and water feed has a mass flow rate of 4,900. Well, the recommendation is that flow rate is not specified at any point, so we maintain the removal of these specifications. There is a third specification, to append new valves and streams. If you double click, you can see that 4 new valves are proposed. These valves are one in the propylene oxide stream. Of course, this valve will be required to control the molar flow rate of this stream. The same for the water feed stream. We also need to control the flow rate of this one. For the mixer out stream, no valve is proposed. The reason is that if you control the inlet flow rates, this is the addition of these ones, so no additional control is required. A new valve is suggested for the reactor products stream, and of course this valve is required if we want later to control the liquid level inside of the reactor. We will try to maintain here a constant level, let's say 50%. If the level goes above this value, we will need to open the liquid exit stream valve, and if it goes below the specified value, the set point, then we will close it. So a valve is required here to control this liquid level. Finally, a fourth valve is proposed to be inserted in reactor vent. However, we do not want this valve, and we are going to uncheck this modification in order to prevent a valve to be inserted here. Why? In our case, this vent stream has no molar flow, as you can see, 0. This connection, it will exist in the real reactor, and it will be connected to a nitrogen line to allow the vapors produced inside of the reactor to go outside. The nitrogen will sweep these vapors and will bring them to a torch or wherever. When the liquid inside of the reactor, the liquid level goes down, some nitrogen is required to enter inside of the vessel to maintain the pressure, because if this line is closed, when the liquid goes down, the pressure inside of the vessel will be reduced. Even the vessel structure can crash because of this reduction in pressure. So, in the simulation, as in the real plant, we do not want to introduce any valve at all in this line, which is connected to a constant pressure line of nitrogen. Well, now all the considerations have been reviewed, and you can click on the button Make Changes. As you can see, you can analyze again the recommendations of the assistant. The recommendation of appending new valves is still remaining. If you double click on it, you can see that the reactor vent valve is again proposed to be inserted, but we don't want to introduce this valve, as we said. If you look at the process flow diagram, you can see that new elements have been introduced. I'm going to move this valve here to make a process diagram easier to review. This valve, this one, and the one of valve of reactor products are new valves. Also new streams have been introduced, for example propylene oxide 1 to connect the new valve with the mixer, water feed 1 and reactor products 1. If you look at the pressure network, clicking on Shift P of pressure, you can see that the pressure at the inlet has been increased from 1.1 to 1.44 atmospheres. Why? The reason is that HDS, when introducing this valve, requires a certain pressure drop to control the flow rate in this system. If you double click on the new valve and click on the tab Rating, you can see that this valve has been designed and a valve coefficient of 16.60 has been calculated for this valve. This value has been obtained from the values at the top of the form. Has been calculated for a valve with a 50% opening, with a delta P, with a pressure drop of 34.47 kilopascals. These two values are established by default by HDS when designing new valves, because a 50% opening allows to close and to open the valve to allow lower and higher flow rates, and this value of pressure drop is high enough to control the flow rate of in the pipeline, but is not excessive to produce energy demand excessive. Well, the rest of the valves have been calculated in the same way. That's the reason why the pressure here has been increased, and in the outlet stream the pressure has been decreased in the same amount. If these values are not in agreement with the real values in your plant, you will need to review them. Okay. It is completed. I tell you, if you click on the dynamic assistant, again the insertion of a new valve in the reactor vent stream is proposed, but we are not interested on this. We need to review if the system is fully specified. To do this, you can click on the bottom Review the equation summary. But in order to do this, we need to move first from steady state to dynamic state. For this purpose, we need to click on the first button of the dynamic ribbon, Dynamic Mode. The system suggests you to use the dynamic assistant, but we have already used it, so we are not interested. And now you are in dynamic mode. There is no return to the steady state. If you want to maintain the steady state simulation file, you need to save it before moving to dynamics. Now the equation summary is available. We click on it. You can do, for example, a full analysis. HDS reviews all the equations, differential equations available, or the algebraic equations, all the variables, and he detects that there are 32 equations, but there are 33 variables. This is not in agreement, so there is a missing equation. This missing equation is can be established within additional specification. If you click on the tab Specified Variables, you can see that only 3 pressures have been established: propylene oxide and water feed in the inlet streams and reactor products. So one value is missing in the reactor vent because all the external streams need to have the pressure specified. To do this, you double click on reactor vent. Here is the form. And you see that the pressure has a value, but this is a calculated value, not a specified value. Specifications in dynamic mode are not determined here, are determined in the third tab, Dynamics. You can specify pressure or molar flow rate. Molar flow rate should never be used. We are going to specify pressure. Now the black value has moved to blue. This means that we can change this value. And if you click again on worksheet, you can see that pressure is a specification in this string. Let's go back to review the equation summary of the simulation. Okay, where? Why it's not working? Let's see. Ever view, Windows, equation summary. Oh, it's here down. Sorry. I need to ask the software to make the review again. Click again on full analysis. And now we have a green status and the number of equations equals the number of variables. So we are ready to do the dynamic simulations. We check that we are in dynamic mode. No, I do not want to go back to steady state. Now I can run the simulation. You can see here on the left bottom, the status is integrator stopped. In steady state, calculations are continuously performed, but in dynamic simulations, you need to start and stop calculations to make the simulation progress. To do this, you need to open the integrator to establish the main parameters. Remember that this is the integration of differential equations in time. Here you have the units of time, minutes. The current time is 0. That means that no simulation has been performed at this time. Acceleration is 1. Probably it's too fast for this process. We are going to reduce it to 0.05. This will reduce the time step for the numerical integration of the system. The end time is when simulation must be finished. Of course, it cannot be 0. I'm going to say, for example, 5 minutes, because it will do the simulation for 5 minutes and will stop. Okay? Now you can click on Start. Pay attention to the status at the bottom. Dynamic Assistant, no. It is usual when you move to dynamics that some warnings appear at the beginning of the simulation. This first one, notice about a possible flipping of phases in the reactor, but we have a single phase, it makes no sense. It also warnings about a possible error in the calculation of the reactor, but it has no relevance. If the error remains, we need to review it, but if not, it is not relevant. Do you want to stop the integrator? No. Okay. And now the simulation is starting and it is stopped. You can see that now the current time is 5 minutes. Okay, I don't want the simulation progress because, for example, the level in the reactor can go above 100% or below 0%, and this will produce a sort of error. If you double click on the reactor, for example, you can see here in the tab Dynamics that the level of liquid at this time is 99%. Okay, this suggests that some problem is still remaining in the simulation. The experience will help you to identify this problem. In this case, the problem is that this stream, we have not specified where it is connected. Inlet streams are defined in terms of pressure, temperature, and composition, but final streams are calculated by the simulation. When there is a reversal in flow rate, for example in this stream, that the flow rate goes in the opposite direction because of increase, for example, in the pressure of the reactor, the temperature, pressure, and composition of this stream is determined by the composition in the reactor because this pipe is coming from this connecting point. In the reactor products, when there is a reversal in the flow of this pipe, the pressure, temperature, and composition is chosen from the last value which has gone out of the system by this pipe. And this is this can be this way because this stream is supposed to be connected to some accumulation vessel, some storage vessel, and when the flow is reversed, the last liquid going to the vessel is coming back to the system. The problem is with the gas venting streams, because in this case, nothing is going out from this stream, and when the flow in this stream reverses, for example, when the liquid in the reactor is going down, some nitrogen needs to enter through this pipe to fill the gap which is produced by the reduction in the liquid of the level. But we have not specified that nitrogen is entering through this stream. So when the is going down, nothing is entering through this stream, and a problem with the pressure system appears. To avoid this problem, we need to specify that this stream is connected to nitrogen. To do this, you only need to double-click on the stream, go to the last tab, Dynamics, and click on the bottom button, Product block. Here we can define nitrogen as the source of material which is entering through this stream. Here is the pressure, the value we have specified. Temperature is 60 degrees because it has been taken from the reactor, but we prefer to specify that nitrogen is at 20 degrees. And for composition, we specify nitrogen. But nitrogen has not been defined in the component list of our simulation. So we need to go back to the properties environment, go to the component list, and here add the nitrogen as a new component. Nitrogen has now been added, and we can go back to simulation. There is a warning because some of the binary coefficients for this component are not present in the database, but since nitrogen is not soluble in the liquid, we are not interested in these interactions. Okay. A warning about changes in the system, and he says, do you wish to update the affected operations? That means, do you want now to consider nitrogen were present in the system? Yes. Of course, since nitrogen is not present at any point, no modifications are carried out at this time. I'm going to modify the composition of this product block. I want to use pure nitrogen for reversal flow. Okay, now I close, and when the level of the liquid goes down here, nitrogen will be entering through this stream. Okay, I suggest you to save this file, and if you have not done until this moment, you can download example 3D to continue with introduction of the level controller.